Okay, beginning of the end. And so I asked, well, to go in and introduce Chelsea for the simple reason that we first met during the pandemic. We were running Code Mesh, so it was a virtual conference which kind of brought together a mix of developers, visionaries, programming language inventors, tool makers, people kind of working with non-mainstream tech, aiming at, solving innovative innovative problems, and I think maybe, kind of sounds a bit familiar. And we were doing a lot. We were really trying hard. It was a virtual conference. It was the height of the pandemic. We were trying to bring the social back to virtual conferences. So basically, what conferences are all about. It's about meeting people, it's about learning, it's about interacting. And yeah, we had, I don't know if you remember it, but we had speakers introducing other speakers. We finished the talks with, we were trying to basically simulate the whole Joe Armstrong effect, For those of you who spoke, when Joe Armstrong was alive, he'd sit in the audience and people would dread it. Oh my God, Joe's sitting in the first row. I hope he won't ask a question. And we've wrapped up all of the talks, with a conversation among speakers, where the audience was welcome to step in and ask questions. And in doing so, I think Chelsea really struck, and it's struck a note because she gave her talk standing up. All of us, speaking, we'd be sitting down, looking at the camera. No, she was standing, moving around, waving her arms, and it's something, it's a trick I started doing. So when the whole program committee, were asked, when the whole program committee, suggested her, I was the first one jumping. Yes, yes, yes. I finally get to meet her in person because I'd only seen her kind of in 2D. She was standing, moving around, but still in 2D. To the point where, we were at the speakers' dinner yesterday, and I didn't recognize her. So that's the reality of it. But, it's, and, well, at the time, I think, you spoke about what makes a programming language. And there was a quote in there which was, the first thing you need to do is make your code maintainable. Don't worry about speed. And that was a quote which I think many of you will recognize, from Joe Armstrong. First make it work, then make it beautiful, and then if you really, really have to, make it fast. And to that I added, in 90% of the cases, it's going to be fast enough. The remaining 10%, you won't have time to make it fast, so, just ship it. So, as a result of that, usually, when we write keynotes, we usually invite someone from outside of the community. But today, well, we're inviting you. I think we're actually making you an honorary citizen of the community, even though you don't work with the Beam on a real, on a day-to-day basis. For the simple reason that that your talk has all of the buzzwords we're kind of used to, and I don't think you were probably aware of it when you put together your abstract. But what you're talking about was what you were talking about is fault-tolerant machine learning operations. And the buzzwords you're going to focus on are the very common ones: resilience, telemetry, braking systems, and deterministic code. Which when you're dealing with concurrency, good luck with deterministic code. So let's hear it for Chelsea. Yeah.
Hi, how are we doing today? We're good. Oh, good. So, as you've heard, my name is Chelsea Troy. I want to start off my time here by thanking you for having me. There's a scholar of programming history in Chicago. His name is Hillel Wayne. He does a blog online. And he did a project a few years ago documenting what software engineers could learn from traditional engineers and vice versa, what traditional engineers could learn from software engineers, civil engineers, and so on and so forth. One of the two most important things that he identified that traditional engineers could learn from us is our conferences. We're lucky and unusual in our field for having conferences like ours where we get together not chiefly to sell or buy, but instead to learn and share. And over the years, I've been to cons for many different programming language communities. Being at Beam this year reminds me very much of the Ruby conferences from the early 2010s. The enthusiasm that radiates from this community in the conversations over coffee and the questions that you ask each other after talks and the way that you introduce your colleagues to the stage is notable and special, and I feel compelled to use a little bit of my time up here to name it because it is rare and it's worth taking a moment to appreciate. My experience with Erlang and Elixir pales in comparison to many of yours. I work in machine learning, and I chiefly code in Python and SQL, and as of recently, Rust. I give workshops about machine learning fundamentals and large language models, how they work and how to work them, chiefly. And sometimes I give talks about the research outcomes we're starting to see at the intersection of large language model usage and developer productivity. That's not the talk I'm here to give today. I'm here to talk to you about machine learning operations. I'm a machine learning operations engineer at Mozilla, and I'd like to talk to you about what I do, which is largely handling the unsexy aspects of machine learning that allow us to deploy and run models reliably in production and mitigate the accidental impacts of thoughtless AI deployment on our constituents and developers. But I want to start with this question. What is machine learning operations? We call it MLOps because if it's not an acronym, it's not important in engineering. Before I go on, I want to take a poll of the room. I imagine not everyone in here is a full-time machine learning engineer or anything, but I'm curious if folks would just raise your hand if you have tried building a machine learning model, or you've watched a tutorial, or you've read a book on the subject. A few people. Okay, fantastic. A plurality, fantastic. So in those sorts of resources, I have found that the topics they tend to cover look something like this. They talk about gathering data, training on data, result validation and testing. They talk about architecture selection, hyperparameter tuning. Sometimes, not even always, sometimes they get into error analysis. And you can do all these steps, and you can have like a kind of a working machine learning model. And then maybe it's in a model file, and you need to figure out, now what? I love this GIF. You will not love this GIF by the time I finish this talk. So this is where machine learning operations comes in. MLOps describes the automation of tasks like updating, deploying, testing the model. Without it, data scientists and machine learning engineers, which also has an acronym, we call them MLEs, they need to manually launch and monitor and support their models in production. The goal of MLOps is to reduce this workload, and the list of things it entails includes a bunch of stuff that you won't find in your standard tutorials, any more than you'll find concurrency concerns in an introductory text for basically any language outside of the Beam. These are the sorts of things that I find myself doing on a daily basis. Operationalizing a machine learning model involves experiment analysis, model selection, building and scheduling training flows. Do you want it to run daily? Do we want it to run weekly? Do we want it to run on a trigger? I do a lot of deploying and running of inference servers. Inference is a word I kind of hate in machine learning because we use it for several different things. An inference server, this is what an inference server is. So when you hear people using this fancy term, you'll know what they're talking about. They mean an API, probably an HTTP API, that a model is behind. And when you pass in the input data that you want a prediction on, the output is the prediction from the model. That's an inference server. Other things that I work on are automated testing for running models and for production data. and sometimes also time and compute optimization. These don't tend to be things that get their own chapters in Introduction to Machine Learning texts. So we're back to the now what slide, in part because I just think it's hilarious. I really like these fish. But also because this is where a lot of machine learning engineering teams find themselves after they figure out how to slap together a model. I've gotten the opportunity to see a couple of talks today showcasing some of the really engaging and fun and useful things that you're able to do with Erlang and Elixir when it comes to machine learning, from NX to Axon to Bumblebee to the built-in concurrency support on the beam itself. The ecosystem has a ton of value to offer the productionization of machine learning models. I'm hopeful, I think, that I can catalyze that effort by offering you a map of the terrain of model productionization and the sorts of libraries that I would love to see for the beam in this area. But enough about you, back to me for a second. When I started doing this work at Mozilla, Mozilla's machine learning efforts comprised a bunch of highly motivated individuals all rolling their own projects all by themselves in their own silos around the organization. I'm sure that sounds very foreign to you. Nobody has run into this problem in the past. But these folks, they were iterating, usually on their own local machines, but sometimes in something like a Google Cloud project, or maybe SageMaker, which is like the Amazon version of that. And they would do this until they had a model that was ready for production, and then they would put it like wherever they knew how to put it, which was of course different for every single team, because of course it was. Mozilla didn't have systematic support at the time for continuous integration or continuous deployment or inference servers. And this wasn't unusual for a company with a nascent machine learning practice. But as teams find more opportunities to leverage predictive and generative models, it becomes inefficient. Similar work gets reproduced all over the organization, and a lot of times it's being reproduced by data scientists or software engineers who don't specialize in machine learning operations. We're really good at figuring out how to get something like C-level working, and if it's not our specialty and it's C-level working, what do? We throw it up there and we stop. We're done. That approach also becomes really undiscoverable because each team is taking on the construction, maintenance, and documentation of their own model deployment pipeline all by themselves, usually in addition to their other responsibilities, of which this wasn't really one of them. So with our engineers overcommitted, we fall back on the minimum working thing. Documentation goes out the window, or we ask ChatGPT to do it and mixed results there. Containerization goes out the window. If building the model on like Todd's local machine and then flinging the file onto S3 gets the thing working, sometimes that's what happens. But each of those choices translates directly into a higher cost of team churn, because when Todd leaves, the team loses a lot of valuable context, in addition to maybe the only machine that ever successfully ran the thing. New entrants then take much longer to understand and run the systems that they've signed on to maintain. I'm going to talk to you about what a more systematic solution would look like. What you're looking at here is the suggestions I get in my search bar on Firefox. And the reason I'm showing you this is that frequently, when I say I do machine learning operations at Mozilla, the first thing somebody says is, oh, Mozilla does machine learning? We do. This is an example of it. These suggestions, for example, come from an API we call Firefox Suggest. It's one of a number of functions in the browser that folks don't always realize does have a machine learning component. Most of our models are internal facing at Mozilla, but we do have a few consumer facing machine learning things. Machine learning models face all the same integration and deployment challenges as standard cloud software projects, except worse, because our input, the data, determines our output, the predictions, and the input here, the data, comes from millions of Firefox constituents. So we have to do a lot more updating to figure out whether our output is correct, and then we have to do a lot more monitoring, because the output could change undesirably without our knowledge. Several schemas exist for categorizing a company's level of machine learning advancement. I'm only going to introduce you to one of them today, and the one I've chosen to describe is the one from Google. And the reason I chose it is because it's the simplest one that satisfies our descriptive needs. I think it's going to give you sort of the introduction to the terrain that I would like you to have. This model has got 3 levels. They all come with pictures, and I'm going to show them to you. Google has documentation of the levels that articulates the technical specifics, but I'll start here at level 0. So at level 0, Todd pulls the data onto his local computer and then uses it to train or change a machine learning model. Once he has a model that he's satisfied with, Todd sticks the model file somewhere in the cloud. Any model retraining happens because Todd does it manually and then sticks the new model file somewhere in the cloud, probably where the old one was. Google's description of their levels has a diagram for this that shows the steps to arrive at the trained model, but this right here is the important part for machine learning operations. Most machine learning projects are here at level 0. If you want to hear a really embarrassing secret, you know, on camera for YouTube, in a keynote in front of the whole conference, at Mozilla, a lot of teams, when I started this work, were not only at level 0, but they were at level 0 using different platforms, because each team came up with their own deployment solution, which gold star for that level of intrepidness. But the thing was, these intrepid engineers had spent time and effort rolling their own systems instead of working on the core efforts they were supposed to be working on. And because of the fact that everybody used a different tool set, working on one machine learning team at Mozilla made an engineer no more prepared than an outside hire to work on another machine learning team at Mozilla, which limited our agility because we couldn't move engineers from place to place. We couldn't even have engineers confer on things all the time because they were using very different stacks. This was expensive, as you can imagine. There are valid reasons to choose one tool set over another, but a lot of times the reason for the chosen tool chain in these cases is something like, Todd had used this one before and we didn't want to burn time onboarding. Or we'd heard of this one and we didn't have time to burn on like tool set research. Makes sense, but ideally we'd like something else. So once an organization is on level 0, hopefully all on the same platform, the question is, it is now what? I'm not going to show you the fish again yet. I'm going to show you this, level 1. This is cut off a little bit. That is okay. The important part is on the slide. At level 1, the model is retrained periodically on new data from production. So that is, a retraining event no longer requires manual intervention from Todd. Todd can go get a coffee. The schematic looks more complicated here, so I'm going to explain this to you. Suppose we want to store a sample of our search terms for insights into our customers' needs, but we don't ever want to store search terms containing personally identifying information. Of course, it's important, so we have an acronym for it. The acronym is PII. And you can think of personally identifying information as things like a name, an address, a credit card number. Y'all would be shocked what people will put in a search bar. I am serious. So we make an algorithm that spits out a prediction of the probability that the term contains PII, and if that probability is above 0, we do not save the term. We want to retrain the model periodically on new search data. At level 1, maybe on a weekly basis, we pull in a sample of the search terms that people have typed in from the last 7 days, and we rerun the training pipeline with that new data. To do this, in addition to automating the training step with the cron job or a directed acyclic graph, we have an acronym for that too, we call them DAGs. In addition to that, we need to add some components to check for things that could go wrong, right? Because now we're retraining on production data. Like, what if the new data produces a model that gives us less accurate predictions than the old one? As I mentioned to you, one of the things that our model does is identify if there is a name in the search term. And if there's a name in it, then we don't want to save it. Say the data for 1 week includes 300 billion searches for a TikTok meme about pulling a Douglas Diggory. And this is based on something that some guy named Douglas Diggory did, and now the model is either categorizing all of those as personally identifying information because it looks like a name, or not categorizing it as personally identifiable information because it's everywhere, except the problem is it is somebody's name. Before we deploy the new model, we want a data scientist to check on this Douglas Diggory thing, at a minimum, right? It's possible we don't want to deploy the new model at all. We also need to add data validation. Suppose our original model checks for names using a named entity recognizer trained mostly on English and Spanish language examples. Suppose that's fine at first because we're building our search insights database exclusively from searches done in countries where people are mostly searching in these languages. So far, so good. At some point, a product decision gets made unbeknownst to the machine learning engineers, who are not frequently included in product decisions, yet. And that decision is to expand our search insights database population to include part of Asia, or part of another area where folks are doing a lot of searches in a language other than English or Spanish. Suppose now the model doesn't recognize names in this language that it has not been trained on. And now searches with personally identifiable information in them start getting saved to the database. A data validation step can check the language proportions of the incoming production data. And if they fall outside of the expected ranges as the demographic exposed to the model changes, we again can alert a data scientist to immediately review how the model works. These steps require a thing called model orchestration. This is tooling that divides the machine learning pipeline into steps like data acquisition, data validation, model training, and model evaluation, and then allows for the automation of those steps, preferably on a cloud machine rather than someone's laptop. A model orchestration library like this makes it possible to go from sort of a toy version of machine learning engineering to productionizing huge models for large populations with all kinds of complications, like the ones that I face generally in my day job, which have to do with the fact that we're trying to train machine learning models, which are generally pretty data hungry, and I'm doing it at a company that's brand relies on deleting data by default. Everywhere has its own version of their one weird thing that they have to do with their production machine learning models. And model orchestration makes it easier to do those things. Right now, for example, Mozilla has a few models that retrain and redeploy automatically. The system is, as in many other cases, hand-rolled by the team in charge of the product. The machine learning operations team and solution has allowed those teams to more easily reach this sort of level 1 complexity milestone, which is really exciting. But again, I will ask you the question. So what? That's right, now what? I will again spare you the fish. Here we are at level 2. If level 1 is about automating the retraining process for an existing model architecture based on new data, level 2 is about automating the process of evaluating different model architectures and options. Maybe the machine learning engineers want to try extracting some new features from the data to see if they provide better predictive value than the existing ones. Maybe they want to add more layers to a deep learning model, or expand the number of trees in a random forest classifier, or even try a few of these things in rapid sequence and see what works best. At this point, the schematic in the Google documentation has enough rectangles on it that I think it loses interpretive value. But I do find this machine learning pipeline step diagram useful for orienting folks. Now, not only is the model training on new production data while Todd's out getting a coffee, but also Todd and teammates can specify a number of different models to try out, and the pipeline will automatically try them. The analysis step is still manual here, and it should be, because when you're exposing the public to the predictions of an automated system, it's important for someone with subject matter expertise to inspect the merchandise. But this gives teams like ours even more power to produce higher quality data automation products, with even less time and effort investment in trying out all of the alternatives. It's precisely the kind of system for which having concurrency built in would be a huge value add. A system like this cannot be hard-coded to accept a specific model architecture, nor can it expect a specific data schema. So for example, if we want to try new features, a table of data with those features will have different columns than a table that didn't have those features. This amount of flexibility takes some doing, it takes some creativity, and it takes some ingenuity. And having machine learning operations tools really helps with a step like this. So those are the levels of machine learning operational maturity in the model that I wanted to share with you. It has 3 levels, but they are, of course, 0 indexed because we are programmers. 0, 1, and 2. Now, you have some idea of what different levels of operational maturity buy you in terms of flexibility to manage and improve your model productionization. We've talked a little bit about what kinds of challenges you can expect to solve at an organizational level as you're advancing through these maturity levels. And there are plenty of questions to ask about how to build fault-tolerant machine learning operational systems. There are a few that I find myself talking to people about the most often. And so I've put together the 3 most common ones to talk to you about. First, how do we establish priorities when we don't own the compute that we run on? This is the case for most developers and almost all independent developers, right? So I have found this question to differ the most between machine learning and standard compute availability questions in API design during the training step for machine learning models. This is often by far the most computationally expensive step, and it blocks the availability of any kind of model for serving a prediction. So through products like Google Colab, AWS SageMaker, and Metaflow Outer Bounds, we can get a hold of bindings to connect to remote compute resources in ways that feel pretty colloquial for folks who have used like a Ruby-ish syntax or a Python-ish syntax or even a Java-esque one, but there's still a number of challenges. First of all, the more compute you need, the longer you might have to wait for the resources you request to become available for you to run your job. Second of all, the more you're trying to do on a limited compute budget, the longer a training job takes. And the thing is, time is money. Perhaps even more importantly, long training jobs mean long feedback loops, significantly slowing down model development and improvement. I find myself prescribing 2 solutions to these teams most often. The first is to have a small, representative pool of training data for training jobs locally. Let's call this the prototype corpus. The point of the prototype corpus is not to actually gauge the accuracy that a model could achieve in the configuration trained on the prototype corpus. The point is to see that it runs, catch runtime errors early, and identify obvious parsing or formatting issues before running the model on big machines with a lot more data. You would be shocked at how many times machine learning teams' timelines get set back 6 weeks because the team keeps debugging tiny blocking issue after tiny blocking issue by firing off the training job on a full data set and waiting 3 days to find out that it did not work. The second situation I find myself prescribing most often is still in the year 2025 to focus on the part that actually needs a model. As trendy as it currently is to attempt to automate entire workflows, it tends to be no slower or less accurate to manually handle the steps that have deterministic outcomes, and then scope down the product from a model that uses an LLM to do the following 16 steps to 6 deterministic intake steps, a small sequence-to-sequence model for handling topic categorization, and then a regression model run on the tabular portions of the input to come up with some estimates for future expectations. A lot smaller, a lot less compute, can accomplish the same job. People hate this advice. The thing is, this is even what OpenAI does with ChatGPT. It's what Google does with Gemini. It's what Anthropic does with Claude. Your input isn't just shoveled directly into the gaping maw of a large language model. Several pre-processing steps determine exactly how to send your request to a model, with what hyperparameter configuration, and which model it should be, to both minimize compute requirements and maximize the likelihood of a useful result. If they need to do it, we probably do too. The second question I find myself answering really often goes something like this: how do we ensure that our models are working properly in production? And the answer here is complicated by the fact that level 1 of the machine learning maturity model prescribes training on production data, so that those inputs could not only break the system, but also change it in hard-to-track ways. My favorite mechanism for dealing with this probably won't surprise you, because it's good old including customer feedback mechanisms at the point that the model product is delivered. You see this in the user interface for auto-generated responses in Gmail that allow you to select from several options. You see it when ChatGPT permits you to select from one of 2 responses. You see it on customer service pages that ask you if the response you just read was helpful. This remains, in my experience, the gold standard. Sometimes logistical hurdles prevent such an option. For example, on Firefox, our options are limited by the fact that we don't connect searches to individual users. We only connect them to sessions in the interest of data privacy. We also actually don't even save searches that we suspect of containing PII, as you know, and so the model that we use to detect that is extremely sensitive. It throws out a lot of perfectly innocuous search terms in the interest of ensuring that we don't save anything the slightest bit personal. To improve that model in production, we have to solve not only for the fact that we don't have user identification data, we have to solve for the fact that we're deleting a big swath of the data outright. The way that we manage that is to profile our training data for critical characteristics, features with high feature importance for detecting PII. Things like numbers, @ symbols, query length, capitalization proportion, and, as we talked about before, presumed language of the queries. And then we check on a daily basis that the search terms that came in, regardless of whether they were saved, follow the same distribution as that of the training data. If it didn't, a team of data scientists get an alert in their inbox, and then usually they email me to ask if it's something we really need to investigate, and I say yes. And then they investigate we keep a 1% sample of the raw search data, which we save for 14 days before we delete it outright, instead of most of the raw data, which we save for no longer than 48 hours before we delete it outright. This profiling mechanism is the one that I recommend to teams performing mature machine learning operations on sensitive data. And it's one that benefits from a language ecosystem with really robust stats packages. The third and final question I've got for you today is an outgrowth of the prior question. How do we make consumer feedback and accurate telemetry first-class concerns? Believe it or not, most of what I've learned about how to do this effectively does not come from working on machine learning operations. It comes from teaching in the master's program in computer science at the University of Chicago. I teach some electives and I also teach Python programming classes. And I regularly survey my students. It's the thing for which I have become notorious. I give them 19 surveys over the course of our 9 weeks together. The more the students participate in my surveys, and the more complete qualitative responses they supply, the more I can improve my class based on their replies. For quantitative responses, the more specific my questions and the less effort they take to answer, the more replies I get. This is why Gmail has you choose from 3 responses and ChatGPT has you choose from 2. You're a lot more likely to click on an option than you are to write a paragraph about your impressions of the 2 responses. This is also why most customer feedback surveys have you select a star on a slider and very little beyond that. For qualitative responses, which are some of the most valuable in terms of getting consumer feedback, I find that the more evocative my questions, the more complete replies I get. When I'm asking for written feedback, I do not ask, what was your experience with using this product? I ask, were you able to find the button to click through to whatever page it is that folks went to? Believe it or not, the more specific I get, the better answers I receive. People understand which parts of their experience I'm evaluating, and they have very specific feedback to share, usually. I value both quantitative and qualitative customer feedback far, far more highly than I value triangulation from telemetry like conversion rates or click-through rates, because I don't have to make guesses about what that feedback means. And the entirety of telemetry interpretation is a guessing game, and it's rife with survivorship bias as well. This is an area where I believe the industry standard to be pretty far behind the minimum viable product, let alone the cutting edge. And so I don't use that industry standard as a starting point for this. Instead, I use my own research questions as a starting point. What do I want to know about how people are using these predictions? And what do I want to know about whether they were useful? What feedback mechanisms can I weave directly into the user experience to gather the information that I would need in order to answer my own questions? Great. Now, who do I need to convince to let me push the PR that does the weaving? They're back. By implementing machine learning model cycles driven through retrospective, customer-supplied data, I can get machine learning engineers a lot more information about what experiments to run. When I have first helped them orchestrate their models in such a way that running experiments feels like a relatively light lift, the data proves more empowering than disheartening for them, because they know that they are able to run these experiments with relatively little effort. Machine learning operations helps machine learning teams answer the question, now what? Not just at the point when the notebook exports its first viable model, but at each point after that in a model application's life. Thank you so much for your time. I'll yield the floor to questions in a moment if I have time. I'm happy also to hear from folks via email if you've got further questions. This is my email address right here on the slide. Please give me about a week to respond. Life is kind of a lot right now, but that's where you can find me. This URL is my blog. I am also on like Twitter and Mastodon and LinkedIn and these things. I just don't check them very often, so LinkedIn is the best way to get me. Capiche? Amazing. All right, I will yield to questions then. Thank y'all.
Any questions?
Everyone is completely satisfied.
Don't be shy. Yes.
Hi, that was an amazing talk. Thank you so much. How can organizations move from level -1 to level 0?
That's an excellent question. I find that, so it's interesting because I think in working as I did, I started this machine learning operations team at Mozilla, and at that time, we were doing, around the organization, folks were doing every kind of thing. And to get from sort of, I'm wondering with -1, are you imagining folks are not using models at all, or are they like on their local machines? Where is -1 for y'all?
Yeah, we have great data, but not using models, and unclear like where models would even be helpful.
Okay, yeah, I'm happy to answer that. So getting from machine learning maturity model -1 to level 0, there's data, but how could you potentially use some of these tools? So I think a lot of the zeitgeist right now around machine learning revolves around like large language models and Gen AI and those kinds of things. And it's fine for there to be zeitgeist, and I'm really glad that folks are excited. And I also believe that there are some useful applications for models like these. But, for example, I work at a place where we use a relatively large number of machine learning models compared to other places that I have worked. And 80% of the models that we use in production are still classical machine learning models trained on tabular data. They are linear regression models. They are decision tree classifiers. They are random forest classifiers. We have a pretty sophisticated Markov model in there, but they're not large language models by and large. And a lot of those sorts of models are relatively computationally inexpensive to run, which mean that and not only are they computationally inexpensive, it's also like a relatively small number of lines of code frequently if there are libraries available for using them. And I think a great way to get started is to go into your data, ask some questions about your data, some things that you would like to predict that you're hoping your data will be able to predict, and try running one of these or several of these relatively computationally inexpensive supervised machine learning models to see whether you can figure out which of the other features in your data carry a lot of feature importance for predicting whatever your target variable is. That can provide you with a lot of information about your data, even if you are not going in with the expectation of being able to build a model and predict things right off of the bat. And they can provide you also if what you need is some tools for convincing an organization to invest here. Having done some of that initial investigation, I find, and establishing what you have learned about your data from working with a machine learning model can be helpful for securing some investment in the opportunity to figure out what features might benefit from a relatively computationally inexpensive approach like this, because frequently I think it's more than people imagine. I think organizations balk at the computational cost of a large language model, which is fair, it's expensive, but in the vast majority of cases I've seen, something much cheaper can provide a lot of value. Does that help? Excellent.
Any other questions? Yep.
Thank you. You said to focus on the part that actually needs a model. So we're sort of splitting a problem into smaller pieces and developing heuristics. This is something that people have been doing for a little while. If I wanted to learn how to do that better, are there resources that you can suggest? Are people writing about this? Or is everybody still just figuring it out as we go along?
This is a good question. Is everyone still figuring it out as we go along, or are there resources that are available to figure out how to split models, or rather to split problems into smaller components? I think that this is an area where we have definitely there's a lot of enthusiasm for building large models that attempt to handle the entire problem. I have found that in splitting it and breaking it down, a lot of opportunity, as I mentioned, for reducing computational cost without sacrificing accuracy. There are a couple of resources through O'Reilly. So O'Reilly has a live course series, and I want to say it's 4 two-hour sessions, and it's called Introduction to Machine Learning Operations. I took it while I was figuring out what stuff wasn't covered on the platform, and I thought that that was a really good one that dove into some of how that works. For most folks who work at tech companies, either your employer will already provide you with an O'Reilly subscription, or I found it to be a pretty easy conversation for like a pro dev expense or something like that. So that's a thing that I would recommend. In terms of books, there is a book called AI Engineering. This is also through O'Reilly. And this book, I mean, it's focused on the big and complicated models, and so it's like goal is not necessarily figuring out how to break down the problem. But I think that it is a good one for getting an understanding of some of the operational pieces that go into this. The last thing that I would say is that it might be valuable as an exercise to take a case study and think about how it might be broken down. An example that I like to think about is news feeds on social media applications. This is one that I've written about on my blog a little bit. So my blog is at chelseatroy.com, and there is a piece on there called "What Do We Do with the Twitter-Shaped Hole in the Internet?" It is a 37-minute read, so strap in. However, one of the things I talk about in that blog post is the fact that Twitter released all this research about how they did this popularity-based news feed, and everyone was like, yes, Twitter, they lead social media, they lead ML in social media, let's all do that. So all the other social media companies copied Twitter, and they made these popularity-based feeds. A couple years later, Twitter comes out with some more papers. They're like, you know what, scratch that, we were wrong. Don't do it like this. Too late. But it's an interesting problem to break down. And one of the things that I do in that blog post is think through, like, how would we incrementally build a news feed with people's actual interests in mind, the topics that they care about and things that they're likely to engage with in a positive way, as opposed to like bombarding them with things that are just going to make their amygdala do backflips all day and all night so nobody sleeps anymore, and then we all spend more time on Twitter. The sort of step-by-step breakdown that I do there, I think, can serve as an example. But I think any relatively complicated process would be an excellent subject matter for an exercise like this. Is that helpful?
Yeah, absolutely.
Fantastic. Okay.
One last question here.
Thank you. So you said it's a problem to get resources to train a large data set. Is it possible to break it up into smaller ones and do like a map reduce where?
Oh, yeah. So this is an interesting question. And I think this is one for reference for the group. The question is about sparing the expense of training on a large data set by doing several small data sets and then doing map reduce, or potentially using a stochastic procedure. We have a number of different ways that we can try to do something like this. Another idea that has sort of come out of, I think, the creation of even more data-hungry models, large language models and things like that, is to try to first do a base training model that collects sort of the probabilities of token-to-token sequences, and then use that data set and train on sort of like the trained probabilities in that model to build something like a logic flow. This is where we still have a lot of, we're not 100% sure what works here yet. But when it comes to computing, trying to figure out how to make predictions from a somewhat smaller data set, this is a thing that I end up doing a fair amount of, not necessarily because of computational costs, but just because Mozilla by design doesn't keep a lot of data. We're not trying to like hang on to people's data. And so there's a lot of thinking about how do you maximize insight from minimum data. And a lot of times it's even through profiles, like the one that I talked about a little bit in the talk, figuring out like what the distributions of things are across aggregate data, and then looking for changes over time in those aggregate distributions can teach us a lot, even if we can't train on the raw data itself. Is that helpful?
Well, I didn't mean to minimize the size of the data. I just meant so you can do it in parallel. And, you know what I mean? If you break up the data and train it and train several models in parallel and then merge them so that.
Oh yeah, you can absolutely do that. So if you're thinking about training, breaking up the data, training models on subsets of the data and then parallelize, you can absolutely do that. It's not infrequently used even in like overlapping subsets of the data for the purpose of trying to get a hold of different characteristics that different models are better at predicting. One of the ways that I see this used most frequently is to train several different model architectures on overlapping data sets, and then use a voting classifier, which can be as simple as every model gets one vote, and then we hand the classification to whatever got the majority of the votes, and can be as complex as giving each model's vote a different weight based on the characteristics that were most important relative to the characteristics that this type of model is good at. So this is definitely an area in which we have some solutions. Does that get more at what your question was? Fantastic. Thank you. Thanks for the questions, folks.
Let's hear it for Chelsea Troy. Thank you so much.